Okay, section 3.2. Here we're going to look at polynomial functions and their graphs in a more general format. We're going to look at polynomial functions, graphs of basic polynomial functions, graphs of polynomial functions with respect to their end behavior, looking at zeros of graphs of polynomials, the shape of the graph near zero, and then local maximum of polynomials. So again, the general form of a polynomial in a standard polynomial form can be written this way. So we have a polynomial of degree n going down with the coefficients in front, subscripted by the n as well to match with the exponent of each variable. So this is the coefficient in front of the term x to the nth power. A sub n minus 1 is the coefficient in front of the term that has x to the power of n minus 1, and so on and so forth. So all of these a's are coefficients, real number coefficients for us for now, and a sub n are a sub naught is the constant of our polynomial, right? It's the only term that does not have an x, or it has an x to the power of 0. Either way you like to look at it. A sub n is the leading coefficient. It's the term in front of the x to the nth term. And then a sub n x to the nth power is the leading term. Okay, so just a little bit of terminology. So here's an example of a polynomial of degree 5, right, since it's the largest exponent. Notice that this is all in one variable. We're only using the letter x in this case. The leading term, the leading coefficient is a 3. The leading term is this little product of 3 times x to the 5th power. The 3, the 6, the minus 2, the 1, the 7, and the minus 6 are all coefficients. And the constant term is this last one of minus 6. Good. So this is a polynomial of one variable, of degree 5 in one variable. And we're going to look at how to get rough ideas, a rough sketch of what this polynomial, or polynomials in general, how we can graph them. That's a really hard thing to do. So it's not like we're going to be able to graph any random polynomial, but certain polynomials are easy depending on the coefficients, and we'll be able to get a rough sketch of how some of them can be graphed. Okay, so some other examples of polynomials. Polynomial in degree 1, otherwise known as a linear equation. Polynomial in degree 2, otherwise known as a parabola. Polynomial degree 3, polynomial degree 4. Okay. So the degrees are here, 1, 2, 3, 4, and they match the powers. If there's nothing written there, by default there's a 1. And then the leading term is the term that has the x with the biggest exponent. And the constant term is the 1 at the end. Right? So a nice little table just to practice finding any of those values. Good. If a polynomial consists of just a single term, then it's called a monomial. Right? If it has two terms like this one, it's called a binomial. If it has three terms like these last two, they're called trinomials. Right? So this is a trinomial of degree 3 in one variable. This is a trinomial of degree 4 in one variable. Good, good. Okay, so if we just focus on monomials, monomials are polynomials that only have one term. Here's some examples. X cubed is a monomial, and minus 6x to the 5th power, that's a monomial. Good. Okay, so graphing some basic polynomial functions. We've already done this before, and I'll revisit it again with Desmos. But we have your standard function where we have p of x equals to x to the power of 0, x to the power of 1, which is going to be a linear equation. Right? So here we have this one, which is going to be the same as a line that fits the form y equals mx plus b, where the m is a 1. Right? This guy right here is a 1 times x plus 0. Right? So it goes to the origin, 0, 0, and it's got a slope of 1. So that's this linear equation, x to the power of 1. Now x to the power of 2 is your standard parabola. And again, we could expand it out to the ax squared plus bx plus c. And clearly the 1 in front of the x squared is the a equals to 1. And because there is no x term or a constant, then we can think of these as zeros. The constant value b was a 0. The constant value c was a 0. Standard line, standard parabola. And then we saw that when we graph your standard x cubed, it has this sort of a shape. And then when we go to x to the fourth power, it looks a lot like our parabola, except it gets a little bit more squared off. We divide it at the point, if we consider the point 1, 1, then as x goes beyond that, then raising it to a power larger than 2 will make it go toward infinity faster. And then for values between 0 and 1, it'll make it grow towards 0 faster. So it squares it off a little bit more, like this. And then powers of 6, powers of 8, powers of 10, all the even ones are going to look more and more like this, just more and more squared off. And same thing for the odd powers. Cutting it off at the 1, 1, to the right of that, as x is values going out to positive infinity, this is going to grow toward infinity faster when we have bigger and bigger odd powers. And for values between 0 and 1, this is going to grow towards 0 faster. So it'll be more and more squared off. Let's look at that on Desmos. Y equals to x to the power of 2. So there's your standard one. Let's put that one in blue. And if we have y equals to x to the power of 4, let's put that one in red. See how it's more squared off? They both go through the point 1, 1, but starting at 1, 1, as we go, as x is values to the right of that, x to the power of 4 is going to grow toward infinity faster, so it's a little skinnier. And for values between 0 and 1, x to the power of 4 is going to grow towards 0 faster. So that's why we have this behavior that happens right here. It just goes towards 0 faster. If we further increase that and do y equals to x to the power of, say, 8, and let's make it really big, how about 10? X to the power of 10, now it gets even more squared off, right? It goes, from this point, from the point 1, 1, as x grows to the right, it'll grow toward infinity even faster, because no matter what input I choose, I'm raising it to the power of 10, it's going to grow toward infinity really fast. And for values between 0 and 1, as I raise them to the power of 10, they're going to grow towards 0 even faster. So the bigger this number gets, the more squared off it becomes. And let's just see if we can do a little slider with this guy. Raise to the power of a. Let's let a be a value between 1 through 20 by 1s. Okay, so, oh, wait a minute. I don't want to do that. Let's make it 2 way. There. So there's the standard blue one. So there's x squared, and then as I raise it to larger and larger even powers, power of 2, power of 4, power of 6, of 8, of 10, it gets more and 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 more squared off, even though there's always going to be a curvature there. To the naked eye, if I zoom out, it might start to look like it's just a rectangle, but it's not. It's always got that little curvature there. Okay? So that's what happens with the even ones. If we look at the odd ones, then something very similar happens. We have y equals to x to the power of 3. If this is our standard, equation, x to the power of 3, then when we have powers of 5, y equals to x to the power of 5, then it's going to get a little bit more squared off. Again, similar to the previous one. So they both still go through the point 1, 1, but to the right of that, x to the power of 5 is going to grow toward infinity faster. And then between 0 and 1, then x to the power of 5 is going to go towards 0 faster. And same thing happens on the other side, except we preserve the fact that they're negatives. Good. So as we raise it from 5 and maybe instead make it a 7, it gets even more squared off. Make it a 9, it gets even more squared off. Make it a 11, it gets even more squared off. Right, so it goes toward infinity faster on this end. Negative infinity goes towards 0 really fast right there. So as we make it powers of a, oh, what the hell? There, so I guarantee that that's going to be a I guarantee that that's going to be an odd power. Then as we change this and make it bigger and bigger and bigger and bigger, it gets more and more and more and more and more squared off. Okay. All right, so that's all we're driving at here. Any questions? No? So as n becomes larger, the graphs become flatter around the origin and steeper elsewhere. So using transformations, we can approximate what's going to happen to these graphs. What happens when we multiply a function times -1? It's a reflection about the x-axis, right? So we flip it upside down. So the normal x cubed function has this sort of a shape, comes this way and comes this way and comes that way along the x-axis. So this is x to the power of 3. Then I know for this one it's going to get flipped upside down. It's going to come this way and come that way. And so for part A, I know it's going to have this sort of a shape. Good. And we can come up with a couple of points to identify where it would go. For this one, I know it's related to, similar to, having a power of 2. And if I had a power of 2, then I know that this would just shift it to the right by 2 units. And then the fact that it's got a power of 4 just means that it gets kind of more squared off, right? So again, we're just doing a rough sketch. It doesn't have to be perfect, but it kind of becomes more like this, more squared off as compared to the standard parabola. And it has this vertex point at 2, 0. Just the sketch. And what about this one? It's a power of 5, so I know it's similar to the power of 3, just a little bit more squared off. So maybe a little bit more squared off as compared to the power of 3. That would make it power of 5. Multiplying it by 2 is going to make it grow toward infinity even faster for values that are, it's going to stretch it vertically. It's going to grow even faster, so maybe a little bit more. Oh, that's really lovely. We'll do it on Desmos in a little bit. The fact that it's a minus flips it upside down, so that's going to change the direction of this thing and make it be more like that. And the fact that I have a +4 shifts the whole thing up. So it's going to be like this, a little bit more squared off than x cubed, flipped upside down and shift it up. Wow, that's really lovely. Let me just choose best. So we had, here's x cubed, and then we have y equals to -x to the power of 3. So it flips it upside down, it rotates it. This point here, this point here travels down to here in the original, and then this point in the original function travels up here. Good. The other one was, okay, that one's easy, we know that one. How about this one? So then we have y equals to x to the power of 5. So see how that compares to the original. Let's make the original in black, and we'll make the new one in red. So the original one is black, x to the power of 5 is this red one. And then if we multiply that by 2, it just makes it go toward infinity a little bit faster. Right, so see what it did there? Multiplied it by 2, makes it go a little bit faster. If we multiply it by -2, it's going to rotate it, flip it upside down. And then we add 4, +4. So it just shifts it up. Shifts it up, flips it upside down, makes it a little skinnier. Okay, so rough sketches. Okay, so monomials, just one term, x to the power of, and we're only going to be thinking about cases for polynomials where the exponent is a natural counting number, 1, 2, 3, 4, 5. And we see that the pattern is pretty easy for those particular cases. Now, some information is going to be provided here that we don't really justify at this moment. It's just something you just have to accept. I think it's pretty intuitive, but we're not really proving it here. So hopefully it's not too disrupting. But I think it's not hard to kind of be convinced that it's true. So first thing is that when we graph a polynomial of any degree, it's going to have no breaks. Here's what a break is, right? Here's a graph, and it kind of comes to an end here, a little break, and then it jumps up, right? There's also not going to be any holes like this. The graph of a polynomial does not have any breaks or holes. It also doesn't have any of these sharp corners like this or cusps. And this is something, again, we're not really proving. We're just telling you this is the case. Whenever you graph a polynomial, polynomials have a great property that they're always smooth and continuous. Pretty little squiggly lines like this one. This is the graph of a polynomial. Or maybe this one. This one's the graph of a polynomial. You're never going to see a polynomial that graphs like this sharp corner. You're never going to see a polynomial, the graph of a polynomial that has a hole in it, right? A polynomial doesn't have any of those things. Without proof, we're just letting you know that that's the case. Okay? The domain of a polynomial is all real numbers for the same reason as this graph implies. It's just a smooth, continuous thing, and it always goes that way and goes that way. Or maybe it comes down this way and this way like this. But there's always, the domain is always all real numbers. The range varies, of course. It could be all real numbers is the range, or it could be some other subset depending on the actual graph. So that one's a little bit more complicated, but the domain is all real numbers. Okay, we're going to look at something called end behavior of a polynomial, which describes what happens as x becomes very, very large in the positive or in the negative direction. To do that, we're going to adopt this style of notation. We're going to use the symbol that x approaches positive infinity this way. That means that the input values into our polynomial are getting infinitely large in the positive direction, increasing without bound. Or this notation, x goes toward negative infinity, means that the inputs to our function, to our polynomial function, are getting infinitely negative, growing in the negative direction. Okay. This notation of y goes toward positive infinity means that the output of our graph is going toward positive infinity. Whereas this one, y goes toward negative infinity, is, as we know, indicating that the output is going toward negative infinity. So we kind of need them as a little pair in order to be able to describe what's happening to our graph. And the order in which you write it, depends on how you write it. But at any rate, so the output could go toward infinity as x goes toward infinity. The output also grows toward positive infinity as x grows toward negative infinity. Right, so this is the behavior that describes what's happening on the outer edges of the graph y equals to x squared. Right, and on the graph y equals to x cubed, then this is what's happening. Y goes to positive infinity as x goes toward negative infinity. As x goes toward positive infinity, and y goes toward negative infinity as x goes toward negative infinity as well. So we're only considering the cases where x is a very large positive number. So as x is a very large positive number, then this is what applies. The output will go toward positive infinity. Y grows toward positive infinity as x grows toward positive infinity. That's describing this up here. Right? And then this over here, way on this side, this one is y is growing toward positive infinity as x is growing toward, oops, not equals, y is going toward positive infinity as x is growing toward negative infinity. But that's describing the behavior of this thing over here as it goes that way, and this one as it goes that way. Good. And something similar happens, but this behavior applies when we have x to the power of 3. Y goes to positive infinity as x goes toward positive infinity, so the same as this one. But then y goes down toward negative infinity as x goes toward negative infinity. Okay. So for any polynomial, the end behavior is determined by the term that contains the highest power of x, because x is large. When x is large, the other terms are relatively insignificant in size. The following box shows the 4 types of end behavior. Okay, so this statement right here is important. Okay, so what that's saying is that if we have a polynomial function, let's say we have a polynomial p of x equals to x to the 5th power, and let's say we have minus some big numbers. How about 35x minus 5,000, something like that. Okay, well, as I come up with the table to try and describe what these things are, x, let's see, if I plug in 0, well, then that's just going to be negative 5,000. That one was easy. As I plug in a 1, I get a 1 to the 5th power minus 35 times 1 minus 5,000. This one's also easy. That's just going to be negative 35,000. 1 minus negative 5,031 gives you negative 5,034. So a big negative number, right? And as we put in different values here, different values of x, these really big numbers here will dominate. Right? There's a big negative there, negative, and there's a big negative there. When x is small, when the input value here is small, these other values weigh in a lot. So we end up getting an answer that's heavily influenced by these other numbers. On the other hand, as we go bigger and bigger and bigger and bigger, and we really think about very large values of x, like let's say x is equal to 19 million. Huge number. All right, well, then we evaluate this polynomial, and we'll have 19 million to the power of 5 minus 35 times 19 million minus 5,000. Now, when x was 0, 1, 2, 3, this minus 5,000 had a big impact on our final answer, right? It was the elephant in the room. It influenced it a lot. But now that we're dealing with big values of x, like 19 million, this minus 5,000, it's like a rounding error. It doesn't really make a big difference, right? So it's not as important to our final answer. Not important. Not as important. I mean, it's going to, if you want to be really precise about your answer, it will have an impact, but not as big of an impact. Not as important. I should say impactful to final answer. And same with this. It used to be sort of an impactful thing that you're taking the input and multiplying by negative 35. So yeah, negative 35 times 19 million is pretty big. But 19 million to the power of 5 is so massively big, so big, that the rest of it almost doesn't really matter so much. It's such a small impact that it doesn't really influence your final answer very much. This is going to dominate what your final answer is going to be. Does that make sense? Think of it like, I don't know, if Bill Gates was my dad and we both lived in the same house, so somebody asked us what is the household income, and I took my income, right? The household income would be me, my income, plus the income of Bill Gates, right? Well, me, my sad little income compared to the massive income of Bill Gates, I mean, I have an impact. If you really want to be precise about it, I guess I changed the numbers a little bit, but really it's all about him, right? I mean, he probably made about $20 billion last year, so compare that with my sad little income, it doesn't really make a big difference. So really, he's the dominating income. What he does is what matters. Or it might not be positive. Maybe he lost a bunch of money on the stock market. You know, maybe he lost $18 billion last year. So minus $18 billion plus my income, we're still at minus $18 billion, right? My income, whether it's, no matter what it is, doesn't really impact things. It's all about him. Did he make $8 billion last year? Did he lose $5 billion last year? That really dominates what's happening. Good? Okay, so when we have a polynomial and we want to think about what happens for very large values of x in the positive direction, or same thing happens when we plug in a very large negative number. What if we want to plug in negative 36,539,432? Right? If I want to figure out what happens here for very large positive or very large negative numbers, it's really the leading term, this guy right here, that determines what happens. It will determine if my final answer is a big positive or if my final answer is a big negative. And the rest of it won't have a huge impact. Does that explanation make sense? Good, good, good. Maybe, kind of. Okay, so when I'm given this guy right here and I'm asked to sketch the graph, remember, sketching the graph does not mean that you get a precise answer. It just means that you do a rough idea of what it is. So far, all I know is that this is a polynomial, so I know its graph is going to be some sort of a wiggly thing, right? Like this, for sure. There are no sharp corners, none, right? Polynomials do not have sharp corners. There are no holes, so this is never going to have like a little hole here and then it jumps, oops, a little hole there and then it jumps up here and then it continues. Nope, not true, not for a polynomial. And there's never going to be just a hole somewhere either. Nope, no holes, it doesn't break, no sharp corners. I know that the graph of a polynomial is smooth and continuous. Good? Okay, so I know that the graph of this is going to be some sort of a curvy, smooth, up and down kind of thing. We're going to do a lot more work to figure out how many of these little bumps and exactly how big and how small they are. So we'll continue to build on that. But for now, we're just going to be focusing on what happens out here in the edges, the outer edges. As x goes out toward positive infinity or negative infinity, does this go this way? Does it go that way? Does it go this way? Or does it go that way? There's really only 4 choices that it can do. Does that make sense? Okay, so end behavior. If we have a polynomial of degree n, then this little image is a little misleading. There might be lots of up and downs here. This thing might go up and down, wiggle, up and down, up and down, up and down. These little dash parts here, we're saying we don't know what happens there. But we're focusing our attention on what happens as x goes out toward positive infinity. As x goes out toward positive infinity, either the polynomial function will go up toward positive infinity, or as x goes out toward negative infinity, the function will go down toward negative infinity. Or the other way around, as x goes toward negative infinity, the function will go up toward positive infinity. Or the function will go down toward negative infinity as x goes out to positive infinity. We see that this behavior is what happens when there is an odd degree, right? Because remember, this looks a little like x to the third power, and this one looks like negative x to the third power. So there's a negative out in front, then this is what the shape will be. And this is going to be the shape of all the odd ones, x to the fifth power, x to the seventh power, all of them. Okay? When the power is even, then it'll look like this, right? Like x squared, x to the fourth, x to the sixth, they will have this shape. So y will go to infinity as x goes toward negative infinity, or y will go to infinity as x goes toward infinity, or y will go down to negative infinity as x goes to negative infinity, or this one, y will go toward negative infinity as x goes to positive infinity. Good. So back to the other case, if I just had some polynomial x to the power of 5, x to the power of 5 minus 35x minus 5,000. I don't really know, by just staring at this, I don't really know the exact graph of this thing. I don't know how many wiggles it has, but I do know that the biggest term, this x to the fifth power right here, is what dominates the end behavior. As we input very large positive or very large negative values into this polynomial, eventually this is going to dominate, right? And so it will lead the behavior. And because it's x to the fifth power with a positive 1 in front, then I know that it's got this sort of a shape. And there might be some wiggles in here depending on what's happening over here. But this is what matters. As x goes out to positive infinity, I know this function will go out this way. And as x goes out to negative infinity, I know this function will go out this way. We'll do a lot more work, and eventually we'll piece it all together and be able to give us like a nice picture of what's happening with this polynomial. So this blue part is still unknown at the moment. At the moment, all we're really looking at is what happens as in the end behavior. Okay, so here's an example. Here we have these guys. What's the end behavior? Okay, all I care about is that the biggest degree is power 4. That's even. That means that if I look at this thing, it's going to be one of these two. As x goes toward positive and negative infinity, the outputs will both go toward positive infinity, like x squared, for example, or maybe they will both go down to negative infinity, like negative x squared, for example. And because we have a negative out in front, and it's a power of 4, I know that this is going to have behavior that comes down here. I don't know, as x goes toward, so here's the y-axis, here's the x-axis. I don't really know where it, what happens in the middle, but I do know that as x goes down to negative infinity, that this will eventually lead over here, and this will eventually toward infinity, y toward negative infinity. And this, as x goes toward negative infinity, y will go toward negative infinity. That's all I know so far from end behavior. As you might imagine, that's not enough. We want more information, so we will be building on this. The next thing we want to know is, well, exactly what does the rest of this graph look like? And so, we're going to come up and we're going to figure out where it crosses the x-axis, if at all. How many bumps and wiggles does it have? Maybe it looks like this. Here is one possible situation of what it might look like, right? I don't know. I'm not saying this is the answer. I'm saying we're going to build to be able to figure out a rough sketch like this. But end behavior, right now, all it cares about is what happens as x goes toward negative infinity, or what happens as x goes toward positive infinity. And that's what we know here with these little red arrows, right? And it's all about the leading term and the power of the leading term. No? So here is the graph. Okay, see how as x goes toward negative infinity, the graph will go down toward negative infinity, and it'll come this way. So this is what we knew from end behavior, just the little tips. Everything else, well, eventually we'll get a better idea. We'll need to figure out when it crosses the y-axis, where it crosses the x-axis, the x-intercept points. We need to figure out these little bumps here, how many local maximums, local minimums there are, inflection points, right? So all kinds of more information will help us be able to build up to be able to do this whole graph. But for now, we're just looking at end behavior. Good. Okay, another important thing that we want to look at is something called the zeros of a polynomial. I'm sure you've run into these before, even if you didn't call them zeros. So real zeros of a polynomial go by different descriptions. There are 4 different things that describe exactly the zero of a polynomial, what it is to be a zero of a polynomial. They're all true, equivalently true of a polynomial. And we can, if we know one of these is true, we know all of them are true. Okay, so if P is a polynomial and C is any real number, then the following are all equivalent. C is a zero of the polynomial. Okay, we use that language a lot. X equal to C is a solution to the equation P of X equals to 0. Right, so that means that when we plug in a C into our polynomial, the output is 0. Good. That also means then that X minus C is a factor of P of X. That third one maybe is not as intuitive. We'll see how that plays out in a little bit. And then the last statement, that C must be an x-intercept of the graph. And I think number 2, statement 2, and statement 4 kind of match up. Those might be easier to see. Okay, let's look real quick at an example and how all of these apply to it. Oops. Well, okay, so say we're given this polynomial. Note that if we factor it, then this polynomial can be written as this polynomial. I'm sorry, as this product. And from this case, we can easily see some of these things. So let's look at the number 2, for example. We could say that 2 is a zero of P. All right, well, that's just the language we use. X equals to 2 is a solution to this equation equaling to 0. If we replace x equals to 2 here, 2 squared plus 2 minus 6 is 0. If we replace a 2 here and here, we end up with 0 times 5, which is 0. So it is true that x equals to 2 is a solution to this polynomial equaling 0. Because this polynomial was factored into this product, then we can say that this polynomial can be divided by x minus 2 and get another polynomial, right? X plus 3 in this case. So x minus 2 is a factor of that, with remainder 0. And because we saw that x equals to 2 is a solution to this, we get the ordered pair 2, 0, which then is an x-intercept point of our polynomial. Right? All these statements can be repeated for x equals to negative 3. Any questions so far? No? 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 Okay, we will revisit this a little bit more in the very near future, but we're going to be relying on some of this for the rest of this chapter. So we'll revisit in a little bit if there's more questions and there's some more examples in your homework. For now, moving on to the intermediate value theorem. So if P is a polynomial function where P of A and P of B have opposite signs, then there must exist at least one value C between A and B such that P of C equals to 0. There's a nice picture here to describe exactly what that statement is saying. Okay, so we're letting P of X be some polynomial. So we know it's some sort of a squiggly thing. We know that the graph of a polynomial does not have any holes. We know that a graph of a polynomial never jumps. And the graph of a polynomial is always smooth and continuous, no sharp edges. So this red one is just some abstract idea of what the polynomial could look like. So here's a case of a polynomial. Now let's say that we know that at point x equals to a, the output is definitely negative. And at point x equals to b, the output is definitely positive. Thus, P of A and P of B have opposite signs. One is positive and one is negative. If that is the case, then the intermediate value theorem tells us that there must exist at least one value C such that P of C equals to 0. Right? Another way of saying that is that if the polynomial is known to be negative outputs over here, and we know that the polynomial is known to have positive outputs out here, then we can conclude that the graph crossed the x-axis at least once. It might have crossed it more than once, but it crossed it at least once for sure. Good. Questions, 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 questions? So it doesn't have to be this, right? It could be any polynomial. So let's say we have another one over here. So if I have some polynomial, and I told you that at point A, oops, I shouldn't put it in red. Let's say that at point A, it's definitely over here. I test a bunch of points. Here's negative 3, negative 2, negative 4. At these points, it's over here, right? And the outputs are positive. And then maybe somewhere at, doesn't have to be that far. How about negative 1? Let's say starting at positive 3, positive 4. Over here, I know that I'm getting like negative answers. Right? The outputs are negative over here. The outputs are positive over there. They're positive signs. What I can conclude is that this thing must have crossed the x-axis at least once. Maybe it did it more than once. Maybe it looks like that. Or maybe it came down and wiggled, and then came down, maybe. So maybe it crossed the x-axis lots of times. But it had to do it at least once. Maybe it came down and did this. It had to do it at least once because there's no way to go from having outputs that are positive to having outputs that are negative without crossing the x-axis, unless you have a break or something, like you have a hole or a break or something. But we know that that's not true with polynomials. Right? Polynomials never have holes and they never skip. Does that make sense? Good. Good. Okay, again, there'll be some homework that asks you to apply that. But we bring all those things together now to get a rough sketch of what a polynomial function will look like. So first of all, when you're given a polynomial function and you're asked to sketch the graph, we first want to be able to try and factor the whole thing so that we can find the zeros of the polynomial. Remember, the zeros are the same thing as the x-intercept points. So once we find all those x-intercept points, then the next thing we want to do is take some test points in between each segment of the number line that is between the zeros. Right? So the zeros will break up your domain, your x-axes, into little regions, and you want to pull 1 point from each region, plug it into the equation, and determine whether it's positive or negative in that region. You don't even have to find the exact answer necessarily. You just have to know if it's positive or negative in that region. Next, you look at the end behavior by looking at the leading term of the polynomial. That'll tell you the end behavior. And from all those things, you can begin to put together a pretty rough sketch of what the polynomial will look like. Okay. So here, for example, the first thing we want to do is factor this guy. This isn't too bad. Factor out an x. We'll end up with x squared minus 2x minus 3. Good. And then we want to factor this guy. So that's x, and then x minus 3 plus 1. Right, multiplies, adds, there we go. Okay, so this equals that, and this equals that. And now the zeros. This must mean that from here, x equals to 0 is one solution. X equals to positive 3 is another one. And x equals to negative 1 is another solution. So that means that these are the zeros. This is the language we use. Zeros are these guys, 0, 3, and negative 1, which means that the x-intercepts are 0, 0, 3, 0, and negative 1, 0. Okay. On the number line, this turns it into 0, 0 there. That's going to be one ordered pair. Another ordered pair is over here at negative 1, and another ordered pair is going to be over here at 3. So I already have 3 points of my graph. This point, and this point. I already have 3 points. Okay? Because of the intermediate value theorem, there are no other ones in between here. The actual graph, whatever it does here, it's going to do it on one side, either above the x-axis or maybe below the x-axis. One or the other. It's never going to go down here and then all of a sudden pop up and do something over here. Because why? Because then we'd have another 0, and we've already found all the zeros. Okay, so that's how the intermediate value theorem helps us with this. It guarantees that once we find the zeros of our graph, there are no other zeros. We also know that the graph is smooth and continuous, which means that whatever this does, it's not going to do like a weird sharp thing like this. It's going to do some sort of a smooth, curvy thing. And most of the time what it does is the easiest thing. It's just going to do a simple curve. Now, I don't know if it graphs it like this, or if it graphs it like that, or if it graphs like that, right? I don't know how high it goes. And at the same time, I don't know if it does like a weird little thing like that. Maybe it might do something like that. Okay, but for now, we're just kind of building on our knowledge, and so far I know that these zeros are true. Next, we're going to grab test points. Grab a test point in each one of these regions. A test point there, a test point there, a test point over here, and a test point over there. And all you want to know is if the graph is positive or negative there. So let's just pick some easy ones. Why not? As easy as they can get. So here, let's say negative 1/2 is the easiest test point I can think of in this little region. Over here, positive 1 is the easiest one I can think of in this region. 4 is the easiest one I can think of in this region. Or maybe, I don't know, sometimes 5 could be an easy one, or maybe 10. These are all common values people choose. That is definitely in this region. Also, you might want to look at your original polynomial to see which one you want to work with. And then over here, another easy test point is going to be 2, -2. Okay, so then just create a little table and evaluate those results to see whether the results are positive or negative in each one of those regions. For example, for -2, we would end up with -2 raised to the power of 3, -2 squared, and -2. So this would be negative 2 to the power of 3 minus 2, negative 2 squared, minus 3 times negative 2. So that's going to be negative 8. That's going to be negative 2 times 4. That's also going to be negative 8. And then that's going to be plus 6. Okay, plus 6. Okay, well, I really didn't even really necessarily care for the answer. I just want to know if it's positive or negative. And now I know that this is negative. So I've concluded that the graph must be down here somewhere. And then it goes up and reaches this point there. Good. Now I grab a test point from in here, and again, I only care whether it's positive or negative. So instead of plugging it into here, I'm going to plug it into here. It makes it a little easier. So I'll have negative 1/2, and then times negative 1/2 minus 3, times negative 1/2 plus 1. Negative 1/2, negative 1/2. And remember, all I really care about is whether it's positive or negative, because I want to know if this graph is going to continue and be up here in the positives or come down here and be in the negatives. So if I keep track of the signs, I know that I end up with a negative, because a negative 1/2, times another negative, because this is going to be negative 1/2 minus 3. And then 1/2 times plus 1 makes it a positive. So I know that the answer ends up being a negative number times a negative number times a positive, and I know that that ends up being a positive. Positive. So I know that this graph is going to be somewhere over there like that. Again, I don't really know if it goes way up here and comes back down. I'm just saying this is my rough guess of what it does. But plugging in a 1 into here, okay, so plugging in a 1, I get a 1 times 1 minus 3 times 1 plus 1 . So that's going to be a negative from here times a positive times a positive. I know it's negative in this region, so I'm guessing that it's going to look like that. And then grabbing a number from over here, a big number, how about 10? 10 is positive. 10 minus 3 is positive. 10 plus 1 is positive. It's just positive times positive times positive. I know that this graph is going to be in the positives, and maybe it goes that way. Also, keeping track of end behavior, it matches what I expected. Remember that end behavior for very large values of x is going to follow this leading term, so it matches what I expected. As x goes toward positive infinity, the output goes toward positive infinity. As x goes toward negative infinity, the output goes down toward negative infinity. Any questions about that? No? We factor it, we break it down, think about end behavior. We know that its leading term is power of 3, so it's going to have that leading behavior. We can test different points and put it on the table like this. Or like I said, you only really need to figure out whether it's positive or negative in each one. So sometimes we do a little table where you just put pluses and minuses to keep track of the signs. So the next thing we're going to look at is the shape of the graph near 0. Okay, so in general, if c is a 0 of the polynomial, and the corresponding factor x minus c occurs exactly m times in the factorization of m, then we say that c is a 0 of multiplicity m. Good. We'll see an example in a second. By considering test points on either side of the x-intercept, 0, c, 0, we conclude that the graph crosses the x-axis at c if the multiplicity m is odd, and does not cross the x-axis if it's even. Good. So let's look at. So there's our screenshot that gives us the general rule. If we have a 0 of a polynomial with multiplicity m, then the shape of the graph of p near c follows the following rule. Okay, so this is saying that if we're given some polynomial, p of x equals some big ugly thing, x to the 6th power, 5x to the 4th power, plus some ugly thing. But let's say that after I factor it, the whole thing turns out to look like this. To the 3rd power, x plus 1 to the 2nd power, x minus 5 to the 4th power, I don't know, something like that. Well, let's just leave it to like that. Okay, so let's say that that's how it factors. It factors like this. This is saying that the zeros are positive 2, negative 1, and positive 5, right? These are the values that will result in the polynomial equaling 0, right? If I replace this x with a 2, all these x's with 2, I will end up with 0 times something, so therefore the whole thing will be 0. But moreover, this is what they mean by multiplicity, this power 3. This guy, and also, well, even if it's not there, by default, there's like this little invisible 1 there. 1. This is the multiplicity. The multiplicity. So we'd say that 2 is a 0 of multiplicity 3. 2 is a 0 of multiplicity 3. Okay. And we'd say that 2 is a 0 of multiplicity 2. Good. And 5 is a 0 of multiplicity 1. Of multiplicity 1. Okay, and so this theorem is saying that if we have an odd multiplicity for the 0, then the graph is going to punch through to get to the other side of the x-axis. Right? The fact that it's a 0, it means that it's a point on the x-axis. So when I graph this one, I know for sure it'll go through the point 2, 0. Right? When I do like a rough sketch of this graph, here's this. I know for a fact that the point 2, 0 is going to be on my graph. I know that the point -1 and the point 5. So here's 5, here's -1. Here's -1, here's 2, here's 5. Because these are the zeros, I definitely know that these 3 are the places where my graph crosses the x-axis. These are definitely 3 points on my graph. This is saying that because the multiplicity is odd at 2, it means that my graph will either come from this direction and punch through to the other side, or maybe it'll come from this direction and punch through to the other side, okay? Because it's odd. Because the multiplicity, wait, what did I do with, oh, this is a mistake? Oh, this should be -1. Nobody said anything. This right here should be a -1. -1 is a 0 of multiplicity 2. Okay, so multiplicity 2 is even, which means that it'll do one of these things. So I'm guaranteed that when I see the graph of this, either it'll come down, touch it, and then come back up, like a happy face, or maybe the other way around. It'll come from this direction, touch it, and then go back down the way it came. Good. It will not punch through to the other side. So the odd multiplicities punch through to the other side, and the even multiplicities just touch it and go back the way they came. Right? At this point, we don't really have a way of knowing whether it's going to be this shape or this shape. We just know it's one of those two shapes when we have an even multiplicity. And we know that it punches through to the other side when we have an odd multiplicity. Good. So again, it's just another little piece of the puzzle that helps us figure out what the graph of the polynomial is going to be. Let's explore that with Desmos for this thing. P of x equals, and then we had x minus 2 power of 3, x minus plus 1 goes to the power of 2, and x minus 5 and an extra to the power of 1. Okay, so here's what the graph looks like. Zoom out a little bit. Comes down, goes up, comes back down, does this thing. Okay, but we're just focusing on what's happening around the x-axis, the graph near its the x-axis. So here are the 3 zeros, right? It goes through the point -1, 0 because of this thing. It goes through the point 5, 0 because of this thing, and it goes through the point 2, 0 because of this guy. Okay, and then the 2 is a 0 of multiplicity 3, which is an odd one. That means it punches through it. See how the graph comes through on one side and punches through to the other side? Good. Same thing with this one. It has a multiplicity 1, which is an odd power. So it punches through to the other side. It comes through and punches through to the other side. Whereas here, the multiplicity was 2. That's even. So it comes down and just touches that x-axis and goes back up. Right? So that's helping us with the behavior of our function near the x-axis based on the multiplicities of the polynomial. Good. If I change this to be some even power, like let's say 4, see how it changes this? Now it's an even power, so now it doesn't punch through to the other side. If I change it to 3, it's going to punch through now. Comes through and goes right through the whole thing. Good. If I change it to a power 7, it's going to go through the whole thing. Right? Obviously, the whole rest of the graph changes, but right now we're just focusing on what happens with these guys, and it's doing a pretty good job of that. But so if I put a 2 on there, then it comes through, touches, and goes back up. Right? Same thing with this one. At -1, we have an even one. That means that right now it's coming up, touching it, and coming back down. If I change this to a 2, see that's going to do that for all of them. Comes down, touches, comes down, touches, comes down, touches. If I put a -1 out in front, and it's going to flip the whole thing upside down, but still it keeps the same property that it comes through, touches, and comes back down the way it came from, because right now I have the multiplicities all even. Any questions? No? Okay, so now let's look at this thing and do like a rough sketch, putting together the things we know. Let's see, first of all, the zeros. That's going to be easy. Let's put a little table, and we'll put zeros, and the multiplicity. So of course 0 is going to be one of the zeros because of this 0, and it's got multiplicity 4, and then +2 is another 0, and it's got multiplicity 3, and -1 is another 0, and it's got multiplicity 2. Okay, so because these are zeros, that means that I have ordered pairs. I already have these ordered pairs in our graph. So I already have 3 dots in my graph. The point 0, 0, the point 2, 0, and the point -1, 0. Good. On my number line, as I begin to kind of sketch what this is, I'm starting to get a nice idea of what this graph is. I'll use this. Here's the y, here's the x. Okay, so far I have the point 0, 0, and I have the point 2, 0, and I have the point -1, 0. So those are the 3 points I have so far. This breaks up our number line into 1 zone, 2 zones, 3 zones, 4 zones. So I need some test points so that I can figure out what the graph is doing in each one of those sections. Right. So this one was -1, 0, and +2. So let's pick a test point. It doesn't matter as long as a nice simple one from each zone. So let's pick from over here, let's pick a -2. From in here, let's pick -1/2. From in here, let's pick 1. And from over here, let's pick 3. Good, so now I have to figure out what each of those values is in order to solve this. Let me make some room here. Okay, so I need to figure out a table where I need to figure out -2. Okay, so p of blank equals blank to the power of 4, blank minus 2 to the power of 3, and blank plus 1 to the power of 2. And the first one we want to work with is this -2. -2, so -2, -2, -2. That's going to work out to be a -2 to the power of 4. That's going to be 2, 4, 8, 16, +16, times, and this is going to be -4 to the power of 3. That's going to be -64. And this is going to be -1 to the power of 2. That's just going to be +1. So at the end of the day here, we end up with 16 times 64? So -1024. But really the most important part is that it's negative. So I know that my graph is way down here somewhere. Somewhere over here is the point -2, -1024. Good. Okay, so now we figure out a point in between here. So -1/2. P of blank equals to blank to the 4th power, blank minus 2 to the 3rd power, blank plus 1 to the 2nd power. Now I'm going to plug in those -1/2s everywhere. negative 1/2, negative 1/2, negative 1/2, negative 1/2. Okay, and all right, well that's going to be positive 1 to the power of 4, which is going to be positive 1 over 16. This as a mixed number is 7 over 2, negative 7 over 2. Wait, no, 5 over 2. Right, so 2.5, negative 2.5, raised to the power of 3. And this is just going to be 1/2 squared, so that's just going to be 1/4. So that's good and ugly. That's going to be 125 over 8. And 16 times 125 to the power of 8 times 1/4. So 16 times 8 times 4 gets you to 512. So 125 divided by 512 is the other ordered pair. Okay, so the actual value isn't even really that valuable here because it's kind of hard to graph it. I mean, it's, I don't know, close to a fourth when you reduce it. So it's going to be just some dot over here somewhere. So I don't know, maybe around there. That's going to be the point negative 1/2 comma 125 over 512. So we have that point right there. The number 1, evaluate this at 1, p of 1 is going to be 1 to the 4th power blank minus 2 to the 3rd power blank plus 1 to the 2nd power. Plug in a 1 here, 1, 1, 1, and a 1. That's going to be equal to 1 times negative 1 to the 3rd power, which is negative 1, and then 2 squared, which is 4. Well, that one was easy. So we end up with negative 4. Finally, an easy one. Okay, good. And then next, p of 3, 3 to the 4th power, blank minus 2 to the 3rd power, blank plus 1 to the 2nd power. And we're going to plug in 3. So 3 in there, 3 in there, 3 in there, and 3 in there. That gets ugly. 3 to the 3rd power, that's 27. Oh, to the 4th power, that's going to be 81. Times 1 to the 3rd power, that's just 1. And then 4 squared is 16. So it's 81 times 16, 1296. 1296. Good. Okay. All I really care, the most dominant important thing here is that it's a negative value. Here, this is output is negative. Output is negative. So I know that the point is going to be somewhere over here. So I have a point of like 1 comma, I don't know, negative 4 over here. Something like that. 1 comma negative 4. And then over here, the output was positive again. Nice big positive output. So I know that when I graph it, 1296, that's going to be some huge value over here somewhere. Way over here at 3 comma 1296. Good. So we're starting to get a sense of what this graph will look like. And so we can kind of piece it together. And at this point, it is just a guess. But my guess is that it does something that looks like this. Okay. Like that. No. Okay, that goes that way. Or whatever, you get the idea. It goes up, crosses at this point, has a little curvature there, comes back down this way, comes back up that way, and then goes up that way. Right? And that's just a guess. You might wonder, how do I know that it does just like this little thing comes down here and goes that way? How do I know it doesn't do something like this? How do I know the graph doesn't come down, does like a little bump, 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 hit that guy, come back up here, wiggle, 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 and go that way? Well, we have absolutely no evidence to indicate that it does that. So one guess is as good as the other, but I don't know if you've heard of Murphy's Law. Contrary to any evidence, the simplest explanation is usually the correct answer. So that's sort of what happens here. The simplest thing you could do is just have one little bump there and come back this way. And that's usually the answer. Not always, but usually that's what it does. It just comes up, has one little bump, and comes back that way. Good. Okay, so now let's match it up with everything else we know. How about multiplicities? Does it match what we thought about multiplicities? At 0, multiplicity 4. At 2, multiplicity 3. Negative 1. How did I screw this up? What's happening here? 0, 0. Okay, we have this guy. Multiplicity 4. It's not supposed to go through. So this is wrong. It's supposed to touch it and go back the way it came from. But then how come we have a 1 here? 0, 2, and negative 1. 0, 2, and negative 1. Multiplicity at 0 is 4. Multiplicity at 2 is 3. Okay, so this one matches that it goes through. Multiplicity at negative 1 is also not supposed to go through. Did I mess up with the signs here? Negative 1/2 gives you a positive, gives you a... Oh, how come nobody stopped me? I blame you guys. Hello? There's a negative right here, raised to a power of positive 3, which means that this must be a negative, right? It preserves its sign. Here, this was a 4, so that gets rid of it, makes it positive. And here, this is a square, so it gets rid of the sign. So anyway, this is a negative answer. Good. So going back over here, when we graph this guy, this is supposed to be on the other side. It's supposed to be down here. So let's see if we can erase some things without erasing the whole thing. Let's get rid of that. And let's get rid of that. Okay. So it's supposed to be a point like over here that is negative 125. Let's make it blue. Right, so that point right there. Okay, now it matches my multiplicity, right? Because multiplicity at negative 1 was even. It's supposed to just kiss it, just touch it, and go back the way it came from. So now it matches that a little bit better. And then at 0, we also have an even multiplicity. So it's going to come up and touch it and go back the way it came. And then it goes this way, touches that thing, and goes up. And 2 is the only one that has an odd multiplicity, so it punches through and gets to the other side to go that way. And now it matches it. Any questions? So far we're okay? And then the last piece of information we have deals with end behavior. So end behavior, to be able to figure out end behavior, I need to figure out the power of the leading term. So really we'd have to expand this whole thing out. However, I don't really need the entire polynomial. I just need to know what's the polynomial with the biggest degree. So we can kind of sort of begin to FOIL it all out. So let's do it this way. Space. Okay, so I have p of x is equal to x to the power of 4, x minus 2 to the power of 3, and then x plus 1 to the power of 2. Okay, if I FOIL this guy out, that's going to be easy. Let's just do that guy. That'll be x squared plus 2x plus 1. So that takes care of this. And then there are these terms. Let me rewrite it as x minus 2 times x minus 2 squared. We know how to expand that. So this will be x to the 4th power. Let me go ahead and expand this. This distributes easily into there. So I'm distributing this into here and this into here. So I'll end up with x to the 5th power minus 2x to the 4th power, and all of that still needs to be multiplied by x minus 2 to the 2nd power times x squared plus 2x plus 1. Okay, and then as I FOIL this, well, okay, let me FOIL this guy out. That one's not going to be difficult either. This guy by itself is x squared minus 4x plus 4. Right, that's this thing. Don't worry, we're not going to FOIL out the entire thing. I just want to see what the leading term is. And the leading term only cares about the biggest degree. So we'll end up with these guys. Okay. As I begin to FOIL these two out, right, as I'm going in the process of trying to figure these out, I'll start FOILing these. But if I'm just interested in figuring out the biggest term, it's really just going to be this times this. Right? So as I begin to FOIL it all out, I know that I'll get the term x to the 4th power from these. And then from those two, I'll get plus 2x to the 3rd power, right? Plus x squared, right? Minus 4x to the 3rd, minus 8x squared, right? So that's the beginning of this whole FOILing process. All of that still needs to be multiplied by this x to the 5th minus 2x to the 4th power. So when I FOIL this guy out, again, I'll have to multiply this times this, and this times that, and this times that over there, and then later this times this, and this times that, and this times that over there, and dot, 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 dot. But as I begin that foiling process, the biggest term is going to come by doing this one times that one. So it'll end up being x to the 9th, and then plus 2x to the 8th, plus x to the 7th, okay, dot, 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 dot. So all that really matters for end behavior is to figure out the biggest term. And the biggest term is going to be that guy, x to the 9th power. Good. 2 of those powers come from here. 3 of those powers come from there. And then x to the 4th. So really we could have seen that it's equal to 7, and 2 makes it 9. So it's x to the 9th power. You just have to be careful of what the constant in front is going to be. Now in this case, it was super easy because they're all 1s. There's a 1 there, there's a 1 there, and there's a 1 there. So we just multiply those 3 1s, and then that's how we get that there's a 1 in the hour, in the biggest power. And then we just added 4 and 3 and 2 to give me a 9. Good. So the rest of it, for the purposes of end behavior, doesn't matter. All I have to know is the leading term, and it's a power degree 9, it's odd. So I know that the end behavior is going to match exactly this. So it just helps us confirm that it's going to have this behavior. It's going to follow the same end behavior as x cubed, as it's going to have y go to infinity as x goes toward infinity, and down here y is going to go toward negative infinity as x goes toward negative infinity. So it's going to match this, right? Because it's a power 9, it'll match the same behavior as x cubed. Remember, x cubed has this sort of shape. Right? So x to the 9th power will be similar. End behavior. Let's see what the author did. Okay, so we have 0 multiplicity 4, 2 is a multiplicity 3, negative 1 is a multiplicity 2. Okay, even multiplicities. The polynomial is degree 9 and has a positive leading coefficient, so we know that it's going to follow that behavior of an x cubed. So as y will go to infinity as x goes to infinity, y will go to negative infinity as x goes to negative infinity. Okay, and then similar process that we do, come up with the zeros, figure out a test point, and then from that we can start to stitch together what the graph will look like. Local maxima and minima, it's going to be, I think we've discussed this before, as we have our graph and we look at all the places where there's like a little bump, either bumps up or bumps down like this. We call these local maximums, local minimums. By definition, it means that there must exist some little region of the domain, some little neighborhood of the domain, where this one is the king of the hill, right? Any other value of x that you choose in this neighborhood, when you evaluate it, it always ends up being less than f of a. That means f of a is the largest value in that little zone. It's not the largest value of our function, because notice, for example, over here, these output values are larger than f of a. But within a little neighborhood, it is the largest value. There exists a little neighborhood, a little subsegment of the domain such that f of a is the largest value. And similar for a local minimum, there exists a little neighborhood, a little section of the domain that contains the value b, such that f of b is the smallest value in that neighborhood. It's not the smallest value of our function. As you can see, all these values over here are smaller than f of b, but there exists this little neighborhood such that f of b is smaller than any other point evaluated, any other value you choose near b and you evaluate the function, you're always going to get that f of b is the smallest in that neighborhood. Okay? So visually we can see it. When we graph it, we can easily spot them where the local maximums and local minimums are. But it takes a little bit more work to figure those out when you have an equation and you have to figure out where those little bumps are. Okay? This next theorem here just kind of helps us identify how many to expect. So if p of x is a polynomial, a standard polynomial of degree n, then the graph has at most n minus 1 extrema, combinations of maximums and minimums. And note that this is at most. It doesn't mean that it has to have that many. It means that it's the most it could possibly have, but it might be less. So this is saying that if we have a polynomial given to you of the form p of x equals to x to the 6th power plus 2x to the 5th power plus 3x, for example, this theorem is saying that it has to have at most 5, right? N minus 1, 5 bumps, right? Local max slash local min. But it doesn't have to have that many. Note, for example, that if I have p of x equal to just x to the third power, according to this theorem, there would be at most 2 local maximum, local minimum. But if we think about the graph of it, there are none. Right? When we graph x cubed, it looks like this. So there are no local max or min in x to the third power. Right? So this is saying at most 2. At most 2 local max, local min. That doesn't mean it has to have any at all. Min. But if I didn't know the graph of this thing, I could definitely tell that there are not 3 maximum minimums, or 4 or 5 or 6. There's at most 2. Okay, graph this polynomial and determine how many extrema are in it. Okay, so don't panic. They're not asking us to hand graph all of these things. They're just saying if we graph them, confirm that it satisfies the theorem for local maximum, local extrema. And so from the theorem, because this is the degree of the polynomial is 4, we know that there must be a maximum of 3 local max, local min. And because this has degree 5, there must be a maximum of 4 of them. And because this is a degree of 4, there must be a maximum of 3 local maximums, local minimums. Good? And that's what this statement is saying. And if we graph them, they're already on here, so let's just look at them. So here is the graph of this polynomial, degree 4, and there is 1 local minimum, 1 local maximum, another local minimum. There are 3 of them. So it satisfies our statement. This is degree 5. There's a maximum of 4, and there is 1, 2, 3, 4. Right? There's actually 4 of them. And then this next one has degree 4, so there should be a maximum of 3, but in fact there's only 1. And that's okay. It's a maximum of 3, not that there has to be 3. Good? Good?